Hello friends, welcome to GMA. Today I'm going to present a video from mathematics from linear algebra, and we are going to cover the topic of system of linear equations. Let us see how to solve system of linear equations using Gauss elimination method. So let us first see what is a linear equation. A linear equation is of the form ax plus by is equal to c. So if you observe here, both the variables are of degree 1. So this ax plus by equal to c represents a line in 2D. If I increase the number of variables, so I can have ax plus by plus cz equal to d. So that would represent a line in 3D and so on. So when you have more equations, you can call it as a system of linear equations. Okay. So all of us know that a line has infinitely many points. It is a collection of infinitely many points. So if I consider an equation of the form 2x plus 3y is equal to 4, then what do you mean by the solution of this linear equation? The solution means all those xy points which satisfy this equation. For example, I may have 2x plus 3y equal to 4. So if I put x is equal to 2, suppose, then my 3y would become 0 and y would become 0. So 2, 0 is one of the points that lies on this line. Likewise, we will get infinitely many points that lie on this line. So when I have number of variables more than number of equations, like in this equation, I have 2 variables and I have only one equation. So I get infinitely many solutions. There are many points which satisfy this equation. So there are 3 types of the solution we may have when we consider any system of linear equations. It may have a unique solution. It may have no solution. And it may have infinitely many solutions. Okay, so usually when your system consists of more variables than number of the equations, you get infinitely many solutions for that system. So here we are going to use Gauss elimination method. What is Gauss elimination method? We are going to reduce the given matrix, reduce the coefficient matrix to row echelon form using Gauss elimination method. And then use back substitution method if possible. If possible. So from the row echelon form itself, we can interpret the solution type of that system. So let us have an example. I'm considering a system say Okay, the question is investigate for what values of lambda and mu the system of equations x plus y plus z equal to 6, x plus 2y plus 3z is equal to 10, x plus 2y plus lambda z is equal to mu have no solution, an infinite number of solutions, and a unique solution. So this is a 3x3 system, right? We have 3 variables and 3 equations. So usually when our matrix is 3x3 matrix gets all 3 leading ones in each column, then we may have a unique solution. So let us see what happens when we reduce this to row echelon form. So let us consider, let A be the matrix of coefficients. So A would be matrix of coefficients of all variables on the LHS of each equation. So those are 1, 1, 1. The first equation is x plus y plus z equal to 6. So 1, 1, 1. Then we have, okay, yeah, here we will not, we will augment our matrix later on. How? Let us see that. Let us first form the matrix of coefficients as A. So second equation is x plus 2y plus 3z equal to 10. So 1, 2, and 3. And the third equation is x plus 2y plus lambda z equal to mu. So x plus 2y plus lambda z. Okay. So these are the variables x, y, z, 3 variables we have. Now let us consider the matrix B as the matrix of constants on the RHS. So matrix of constants on RHS of equations. So in this case, the constants are, for the first equation, the constant is 6, second equation 10, and the third equation it is mu. So we are going to form a column matrix for this. So order of matrix A is 3 cross 3, order of matrix B is 3 cross 1, and in 12th standard you must have seen we used to write this as AX equal to B. But now we are going to use, as you are in the first year, we are not going to use this X, which is the matrix of variables. We are going to augment these two matrices. Augmentation means we are going to combine the columns of A with columns of B. So consider the augmented matrix A colon B. Okay. So let us combine these two matrices and then we will reduce the matrix of coefficients to row echelon form 1 by 1, and the corresponding changes we will make on the constants matrix as well. 1, 2, lambda. And here I'm putting a line just to understand the differentiation between A and B. And my constant matrix is 6, 10, and mu. Okay. So how to reduce this matrix A to row echelon form. So usually we start with the diagonal element. Now here this is 3 cross 3. So in case of 3 cross 3, we will try to get our leading ones. The first position of leading one is A11. So the first element, I will try to reduce it to 1, but it is already 1. So A11 is 1. Therefore, no transformation is required for that. If that number is other than 1, then you will have to divide the whole row by that particular constant to make it 1. So no transformation required here. Now the elements which are below this leading one, this is my leading one. And these two elements which are below this leading one, I want to convert them to 0. I want to reduce them to 0 using this one. And therefore my row transformation would be R2 I'm going to change. So the row in which I want to make the change, I'm writing that row first. So R2 changes to R2 minus R1, simply 1 minus 1 is 0. And R3 also, R3 minus R1, 1 minus 1 will give me 0. And I have to apply this operation throughout this row. Okay, so let us see what is AB now. So the first row remains same. Now second row, 1 minus 1 becomes 0, 2 minus 1 becomes 1, 3 minus 1 becomes 2. Similarly, 1 minus 1 becomes 0, 2 minus 1 becomes 1, and lambda minus 1 is lambda minus 1. The same operations I am supposed to perform on the matrix B as well. So it was R2 minus R1. So 10 minus 6 is 4. Sorry, the first row remains as it is, 6. And second row changes to 10 minus 6, that is 4. And the third row changes to mu minus 6. Okay, so we have got our leading ones here. This is the leading one, and both the elements which are below the leading one, they have become 0. Now the next leading one, so here I will not be able to get the leading one. I am supposed to get the next leading one below this leading one in the next column. That means I have this option open for me to get my leading one. I hope you understand this point, that once you get leading one in A11 now position, we have to get the next leading one below this leading one in the next column. So this position I'm looking for. And if you observe, fortunately, this is already 1 here. But if it is not 1, then you should make it 1 by choosing the appropriate row transformation. Either you can go for interchanging of rows, or you can divide this number. This should be a non-zero number. If it is non-zero, if it is a 0 here, then you should look for the next entry. And if this is non-zero, then you should interchange these two rows. But in this case, this A22 element is already 1. So again, there is no transformation required. So A22 is also already 1. So no transformation is required for A22. Okay, you need not to reduce this A22. It is already 1. But the element which is below this leading one is this. So I should make this one to 0. And therefore, now I want to make, so this was my second matrix, and I want to convert this one to 0 using R2, because this 0 should not be changed. This 0 will be changed if I use R1. But if I use R2, because of these two zeros, the first entry in R3 will not be changed. So I am supposed to use second row to convert this number 1 to 0. And therefore my operation should be R3 changes to R3 minus R2. Therefore my matrix becomes, the first row remains same, the second row remains same, and the third row changes to 0 minus 0, then 1 minus 1, that is 0, which I want, and lambda minus 1 minus 2, which is lambda minus 3. The same changes I am supposed to carry out on the RHS, that is in the matrix B. So the operation is R3 changes to R3 minus R2. Mu minus 6 minus 4. So mu minus 10. This is what I am getting. Now, I am asked here about the possibilities of all types of solutions. When the system has unique solution, when the system has no solution, and when the system has infinitely many solutions. So system will have unique solution if this particular entry is non-zero. This particular entry should not be equal to 0. Then my system would have unique solution. And if this is 0, that will do, I guess. So let us write about, let us interpret about the solutions. So mu can have any value. So whatever number you get over here, that is okay. But this number should not be equal to 0, because in that case, see, if lambda minus 3 is equal to 0, then I will have 1, 1, 1, 0, 1, 2, 0, 0, 0, 6, 4, and mu minus 10. Okay, then this is a contradiction, that your LHS is, this is 0 times x plus 0 times y plus 0 times z is equal to something. So this is going to be 0. And how comes that this is not 0? This value is not 0. Okay, so if you want to get any solution here, unique solution, this value must not be equal to 0. So the system, the first one, the system has, which one we had written the first? No solution. Okay. Okay. So let us first discuss about no solution only. We will go in the same order. The system has no solution. When the system will have no solution? When this is 0 and this is not equal to 0. That means you have the same thing which I had written just now, 0, 1, 2, 0, 0, 0, and you have some non-zero entry over here. This is not a non-zero entry. So let me call this as some P. Mu minus 10 I am replacing by P, which is not equal to 0. So how this is possible? That on the LHS you have entirely 0 values, 0y plus 0z, and that is a non-zero entry. If left hand side is equal to 0, right hand side must be 0 in case of an equation, and therefore system will not have any solution if you are saying that lambda minus 3 is 0. So system has no solution if lambda minus 3 is equal to 0 and mu minus 10 is not equal to 0. So that is lambda is 3 and mu is not equal to 10. In these cases, system will not have any solution. If you write lambda 3 and mu not equal to 10. If you take any other solution, any other value for mu than 10, and if you substitute lambda equal to 3, for example, if I say lambda is 3 and mu is say 4, okay, it is not equal to 10. So 1, 1, 1, 0, 1, 2, 0, 0, and I have on the RHS 6, 4. If I put mu is 4, then 4 minus 10 would be minus 6. So how this is possible that on the left hand side entirely you have 0 over here, and this is a non-zero entry. This is impossible, and therefore system will not have any solution when lambda equal to 3 and mu is not equal to 10. Let us see the next case. Next is an infinite number of solutions. So I'm rewriting the matrix, the final matrix. Okay, I'll make changes over here. Now I want system has, second case, the system has many solutions, infinitely many solutions. So when this is possible, this is possible when both of them are 0. Both of them are 0. That means lambda minus 3 is also 0 and mu minus 10 is also 0. That means lambda is 3 and mu is 10. So let us see what happens if I substitute lambda equal to 3 here. This will become 1, 1, 1, 0, 1, 2, 0, 0, lambda minus 3. I'm putting lambda equal to 3. So this will become 0. Then 6, 4, and mu I am putting equal to 10. So this will also become 0. So my entire last row is 0. So what happens here? I get 0 dot x plus 0 dot y plus 0 dot z equal to 0. So whatever values I will put for x, y, z, I'm going to get an answer. For example, if I put x is equal to 1, y equal to 2, and z equal to 3, then also because my coefficients themselves are 0, whatever values I put for x, y, z, that is going to give me an answer. So 1, 2, 3 is going to be my answer here. Similarly, if I put x is equal to minus 1, y equal to minus 3, z equal to minus 7, I'm going to get LHS equal to RHS. Therefore, when the entire last row becomes 0, we get infinitely many solutions, and lambda minus 3 will be 0 when lambda is equal to 3 and mu is equal to 10. Only for these two values from the real line, system will give me infinitely many solutions. Next, let me just copy the page. Yeah, next, the last case is system has unique solution. So let us see when system will have unique solution. System has unique solution. So system has unique solution when lambda minus 3 is not equal to 0. This value should not be equal to 0, and this may be any value. Mu can have any value. Even though your mu minus 10 becomes 0, that means mu becomes 10, then also system will have unique solution. So basically this number lambda minus 3 should not be equal to 0, and mu can have any value. So lambda should not be equal to 3 and mu minus 10 can have any value. For example, if I put lambda is equal to 4 and mu is equal to mu is equal to say 15, for example. Then my system would become, yeah, if I put lambda is equal to 4 and mu is equal to lambda is equal to 4 and mu is equal to 15, then these values will become, I'm just substituting here, lambda minus 3, so that is 4 minus 3, and this is mu minus 10, so 15 minus 10. And then what happens? Let us see. So it will be 111, 012, 001, 6, 4, and 5. So I'm getting 3 equations. X plus y plus z is equal to 6, y plus 2z is equal to 4, and z is equal to 5. So in this case, I'm getting the value at z equal to 5. Then I will use back substitution method, and I will substitute z equal to 5 in this second equation. This is my first, second, and third. 3 equations. So from third equation, I'm substituting z equal to 5 in second equation. So I get y plus 10 equal to 4, which gives me y equal to minus 6. I will substitute y equal to minus 6 and z equal to 5 in equation 1. So I get x minus 6 plus 5 equal to 6, which gives me x equal to 12 minus 5, that is 7. So my solution would be x equal to 7, y equal to minus 6, and z equal to 5. Likewise, if I put any value other than 3 in equation as lambda in the third equation, and any value in place of mu, any value other than 3 for lambda and any value for mu, that will give me unique solution for the system. So system has unique solution if lambda is not equal to 3 and mu takes any value. Mu takes any value. So friends, we have seen today how we can find out the values for lambda and mu to have different types of solutions. You can follow the same procedure to get row echelon form. Try to get the leading ones from the augmented matrix AB, and remember, whatever leading ones you get, below elements you have to reduce to 0. And once you get all leading ones and all zeros which are below these leading ones, then you can use back substitution technique to find out system of linear equations. To summarize, I will just say that a system may have unique solution, it may have infinitely many solutions, and it may have no solution. So friends, if you like my video, please like, share, and subscribe our channel GMA. Only Maths. You can refer to Only Maths playlist in our channel GMA. Also, please like, share, and subscribe my another channel, Triumph Maths. I have mentioned the channel link in description box also. Thank you very much and have a nice time. Thank you.